Displayed formulae. Organic chemistry is the scientific study of the structure, properties, and reactions of organic compounds. Organic compounds are those which contain carbon. For conventional reasons, metal carbonates, carbon dioxide, and carbon monoxide are not included in organic compounds. Many of the structures you will be drawing are hydrocarbons. A hydrocarbon is a compound that contains only hydrogen and carbon atoms. Organic compounds can be represented in a number of ways. Displayed formulae. General formulae. Structural formulae. The displayed formula shows the spatial arrangement of all the atoms and bonds in a molecule. For example, this displayed formula tells us several things about the compound. It has 5 carbon atoms. It has 12 hydrogen atoms. It has only single bonds. Structural formulae. Extended tier only. In structural formulae, enough information is shown to make the structure clear, but most of the actual covalent bonds are omitted. Only important bonds are always shown, such as double and triple bonds. Identical groups can be bracketed together. Side groups are also shown using brackets. Straight chain alkanes are shown as follows. Structural isomers. Structural isomers are compounds that have the same molecular formula but different structural formulae. The molecular formula is the actual number of atoms of each element in a compound. Compounds with the same molecular formula can have different structural formulae due to the different arrangement of their atoms in space. 2 examples of structural isomers are shown below. Table showing structural isomerism in C4H10. Table showing structural isomerism in C4H8. Exam tip. Remember, only double and triple bonds are shown in structural formulae. Homologous series. A homologous series is a family of organic compounds that have similar features and chemical properties due to them having the same functional group. The functional group is a group of atoms which are bonded in a specific arrangement that is responsible for the characteristic reactions of each member of a homologous series. Table of compounds and their functional groups. Family. Functional group. Name ends in alkane, C, an, alkene, C equals C, ene, alcohol, O, OL, carboxylic acid, Cu, onoic acid, ester, COO, YL onode. Exam tip. Make sure you can identify the functional group for each homologous series. General formulae. The general formula tells you the composition of any member of a whole homologous series of organic compound. For example, all of the alkanes have the general formula CnH2n+2, where n represents the number of carbon atoms. This tells you that however many carbon atoms there are in the alkane, doubling this number and adding 2 will give you the number of hydrogen atoms present in the alkane. General formulae can be used to work out the formula of a compound from different homologous series if the number of carbon atoms present is known. General formula of common homologous series. Homologous series. General formula. Alkane, CnH2n+2. Alkene, CnH2n. Alcohol, CnH2n+1O. Carboxylic acid, CnH2n+1 Cu. Worked example. Questions. What is the formula of an alcohol that contains 5 carbon atoms? What is the formula of an alkene that contains 10 carbon atoms? Answers. 1. The formula of an alcohol containing 5 carbon atoms is number of carbons equals 5. Number of hydrogen atoms, excluding in the functional group, equals 2x5 plus 1 equals 11. Formula equals C5H11OH. 2. The formula of an alkene that contains 10 carbon atoms is number of carbons equals 10. Number of hydrogen atoms equals 2x10 equals 20. Formula equals C10H20. General characteristic of homologous series. Extended tier only. All members of a homologous series have the same general formula, same functional group, similar chemical properties, gradation in their physical properties, such as melting and boiling point. The difference in the molecular formula between one member and the next is CH2. These characteristics are shown below for ethanol and propanol, which belong to homologous series, alcohols. Table of characteristics of ethanol and propanol. Ethanol, propanol, molecular formula, CH3CH2OH, CH3CH2CH2OH, general formula, CnH2n+1O, CnH2n+1O, functional group, O, boiling point, OC, 78, 97, exam tip, Make sure you learn the general formula for each homologous series. Saturated and unsaturated compounds. Saturated compounds have molecules in which all carbon-carbon bonds are single bonds. Examples of compounds that are saturated are alkanes. Alkanes are saturated hydrocarbons with the general formula CnH2n+2. Alkanes contain only carbon-carbon single bonds, so are saturated. Unsaturated compounds consist of molecules in which one or more carbon-carbon bonds are not single bonds. They contain carbon-carbon double bonds, C=C. Examples of compounds that are unsaturated are alkenes. Alkenes are unsaturated hydrocarbons with the general formula as CnH2n. The presence of the double bond, C=C, means they can make more bonds with other atoms by opening up the C=C bond and allowing incoming atoms to form another single bond with each carbon atom of the functional group. Each of these carbon atoms now forms 4 single bonds instead of 1 double and 2 single bonds. Alkenes contain 1 carbon-carbon double bond, so are unsaturated. Exam tip. Remember, saturated compounds have single bonds only. Unsaturated compounds have double bonds. Naming organic compounds. The names of organic compounds have 2 main parts. The stem, sometimes called the prefix, end part or suffix. The stem indicates the number of carbon atoms present in the longest continuous chain of the compound. Number of carbon atoms in the longest chain. Part of the chemical's name. 1. Meth. 2. Eth. 3. Prop. 4. But. 5. Pent. 6. Hex. The end part of the name tells you what functional group is in the compound. End part of the name. Functional group. Organic family. An. None. Contains only C-C bonds. Alkane. Ene. C=C bond. Alkene. Onyl. O. Alcohol. Onoic acid. Cu. Carboxylic acid. Amine. NH2. Amine. YL-onote. CoOC. Ester. Structures of organic compounds. Worked example. Name the following organic compounds. 1. 2. 3. Answers. Butanoic acid. The longest carbon chain is 4 carbons, so the name contains but. The functional group is COOH, so the name contains onoic acid. Propene. The longest carbon chain is 3 carbons, so the name contains prop. The functional group is C=C, so the name contains ene. Pentanol. The longest carbon chain is 5 carbons, so the name contains pent. The functional group is O, so the name contains onyl. Exam tip. Make sure you can draw and name the structures given above. Further naming of organic compounds. Extended tier only. When there is more than 1 carbon atom where a functional group can be located, it is important to distinguish exactly which carbon the functional group is on. Each carbon is numbered and these numbers are used to describe where the functional group is. For example, propan-1-OL is an alcohol with an O functional group. The 1 in the name indicates that the O group is located on the first carbon atom. Careful, there are many times when the numbering should start from the right. This is to keep the numbers as low as possible in chemical names. In propan-1-OL, the O group is located on the first carbon atom. Alkanes. As before, the number of carbon atoms gives the part of the compound's name. Alkanes contain only single carbon-carbon bonds, CC, which means that their name ends with an. Some compounds, like alcohols and carboxylic acids, have an in their name. This indicates that those compounds contain only single carbon-carbon bonds, CC. Alkenes. As before, the number of carbon atoms gives the part of the compound's name. Alkenes contain at least 1 double carbon-carbon bond, C=C, which means that their name ends with ene. The first alkene is ethene because you must have 2 carbons to be able to form a double carbon-carbon bond, C=C. After propene, you must state the number of the first carbon that is part of the double carbon-carbon bond, C=C. E.g., but 1 ene has a double carbon-carbon bond, C=C, on the first carbon in the chain. But 2 ene has a double carbon-carbon bond, C=C, on the second carbon in the chain. Alcohols. As before, the number of carbon atoms gives the part of the compound's name. Alcohols contain an alcohol hydroxyl group, OH, which means that their name ends with onyl. After ethanol, you must state the number of the carbon that has the alcohol hydroxyl group, OH, attached. E.g., propan-1-OL has the alcohol hydroxyl group, OH, on the first carbon in the chain. Propan-2-OL has the alcohol hydroxyl group, OH, on the second carbon in the chain. Carboxylic acids. As before, the number of carbon atoms gives the part of the compound's name. Carboxylic acids contain a carboxylic acid group, COOH, which means that their name ends with onoic acid. There is no need to number carboxylic acids because the carbon that is part of the carboxylic acid group is automatically the first carbon of the chain. Esters. Esters are one of the more challenging compounds to name. Their name is based on the original alcohol and carboxylic acid that they were prepared from. Ester names are confusing because the name is written backwards from the way the structure is drawn. Methyl methanoate. The acid portion of the molecule contains the CO single bond and is colored green. There is one carbon, so this gives the methyl part of the name. The carboxylic acid portion contains the C=O double bond and is colored purple. The is one carbon, so this gives the methanoate part of the name. Methyl ethanoate. The acid portion of the molecule contains the CO single bond and is colored green. There is one carbon, so this gives the methyl part of the name. The carboxylic acid portion contains the C=O double bond and is colored purple. The are two carbons, so this gives the ethanoate part of the name. Ethyl ethanoate. The acid portion of the molecule contains the CO single bond and is colored green. There are two carbons, so this gives the ethyl part of the name. The carboxylic acid portion contains the C=O double bond and is colored purple. The are two carbons, so this gives the ethanoate part of the name. Exam tip. Extended tier students should be able to draw the structural and displayed formulae for all of the compounds written above. Common fossil fuels. A fuel is a substance which, when burned, releases heat energy. This heat can be transferred into electricity, which we use in our daily lives. Most common fossil fuels include coal, natural gas and petroleum. Methane, CH4, is the main constituent of natural gas and is a hydrocarbon. Hydrocarbons are made from hydrogen and carbon atoms only. Petroleum and fractional distillation. Petroleum. Petroleum is also called crude oil and is a mixture of hydrocarbons which also contains natural gas. It is a thick, sticky, black liquid that is found under porous rock, under the ground and under the sea. The location of crude oil. Crude oil is located under the sea. Petroleum itself as a mixture isn't very useful, but each component part of the mixture, called a fraction, is useful and each fraction has different applications. Fractional distillation. Each fraction consists of groups of hydrocarbons of similar chain lengths. The fractions in petroleum are separated from each other in a process called fractional distillation. The molecules in each fraction have similar properties and boiling points, which depend on the number of carbon atoms in the chain. The size of each molecule is directly related to how many carbon and hydrogen atoms the molecule contains. Most fractions contain mainly alkanes, which are compounds of carbon and hydrogen with only single bonds between them. Diagram to show fractional distillation. The process separates the fractions according to their boiling point. Fractional distillation is carried out in a fractionating column which has a temperature gradient. It is very hot at the bottom of the column and cooler at the top. During the process of fractional distillation, the crude oil is heated and vaporizes. The vapors of hydrocarbons enter the column which has a temperature gradient. The vapors of hydrocarbons with high boiling points condense at the bottom of the column. The vapors of hydrocarbons with lower boiling points rise up the column and condense at the top. Properties of fractions. Viscosity. This refers to the ease of flow of a liquid. High viscosity liquids are thick and flow less easily. As the number of carbon atoms increases, the attraction between the hydrocarbon molecules also increases, which results in the liquid becoming more viscous with the increasing length of the hydrocarbon chain. Going down the column, the viscosity of the fractions increases. Melting point, boiling point. As the molecules get larger, the intermolecular attraction becomes greater. More heat is needed to separate the molecules. Going down the column, the boiling points of the fractions increases. Volatility. Volatility refers to the tendency of a substance to vaporize. As the size of the hydrocarbon increases liquids, the attraction between the molecules increases. Going down the column, the volatility of the fractions therefore decreases. Uses of fractions. Refinery gas, heating and cooking. Gasoline, fuel for cars, petrol. Naphtha, raw product for producing chemicals. Kerosene, for making jet fuel, paraffin. Diesel, fuel for diesel engines, gas oil. Fuel oil, fuel for ships and for home heating. Lubricating oil. For lubricants, polishes, waxes. Bitumen. For surfacing roads. Table to show the trends and properties. Fraction. Number of carbon atoms. Boiling point range per degree Celsius. Viscosity. Volatility. Refinery gas. 1 to 4. Below 25. Viscosity increases going down the fractions. Volatility decreases going down the fractions. Gasoline, petrol. 4 to 12. 40 to 100. Naphtha. 7 to 14. 90 to 150. Kerosene, paraffin. 12 to 16. 150 to 240. Diesel, gas oil. 14 to 18. 220 to 300. Fuel oil. 19 to 25. 250 to 320. Lubricating oil. 20 to 40. 300 to 350. Bitumen. More than 70. More than 350. Exam tip. You must be able to recall a use for each fraction as well describe the trends and properties.